Okay, we've just described what the solar system formation was about. We set up the story and we talked about the characteristics of the solar system, and I gave you what the past theories were and the current best theory is, if you will, the party line, as Hal Levinson would say. But now let's take a look, and I also showed you the evidence for it being a natural phenomena, namely that there are lots of pictures that we've taken showing that other stellar systems have these solar nebula disks. So now let me show you the simulations that give rise to why we think this is a reasonable situation. So we start with a cloud, and let's see if we can get these things to play. Here we go. Okay, so what we'll see here is as I cause this thing to play, we're going to have two views of the same thing. This is an edge-on view and this is an oblique view. They're kind of, basically we're going to see the cloud collapse, and as it collapses, we're going to see it turning into a ball in one direction, and it's going to be turning into a disk in the other. Okay, so as an edge on, it's a disk. We don't see much in the way of anything going on. Remember, the solar system is quite narrow as a disk. It's quite small, much thinner than a CD would be. But if we look down upon it, we do see a disk. Okay, so let's go back. Now, let's take a look at, one of the things that had always bothered me was this whole idea of the flattening of the disk and the creation of the disk. I use an analogy of watching somebody making pizza and throwing up the pizza ball in the air and it's spinning around. I've never spent that much time watching pizza being made that way. I always roll it out with a rolling pin, but I suppose it could happen that way. All right, so let's take a look at some of these other simulations. This one is, my favorite. Going to Knott's Berry Farm last time and running the bumper cars. And basically, if you remember how it started, and we'll start it again, everybody is going every which way, right? And then they start, starting to share the angular momentum and starting to go in the same direction. Okay, so that's a sort of natural occurrence. You can also solve the equations as yourselves if you were so desired, and my students in the physics classes have the capability to do these things, but you saw what the simulations did. As you have particles collide against each other, they sort of average the amount of momentum that they have, and so they end up going in the same direction. Okay, so the same thing occurs with up and down motion, and so here we have this case. They start going in the same direction and coalescing around a central region. And this is the video we saw just before, so let's continue on. Now, the other thing that happens is as gravity causes this cloud to collapse, it heats things up. Remember the analogy with pumping up an automobile tire. If you haven't done it before, pump one up and put your finger at the nipple and see just how warm it gets. Okay, so in this particular case, what we want to show or see, basically as you get further away from the sun, it gets cooler and cooler. So here we are, pretty close in. The temperature is hot. As you get further away, it gets lower and lower. That's what the equations or our understanding of the world around us would teach us. Now, the inner parts of the disk are hotter than the outer parts. That's what we're getting across. And the rock in this, if the if the gas and dust is made out of like silicon dioxide or iron or other metals, then it will stay a solid uh, much closer to the protosun than things that are further away, than things like water or methane. Water and methane would turn into a gas here, and so it would be sort of like a cloud sort of surrounding the protostar. And as I get further and further away from the protostar, then these regions, the water and the methane would be in ice. It would be a solid. So it would behave in a similar way as the sand, silicon dioxide, or the iron would up here. Okay, it would not be able to be pushed by the solar radiation very much, and it would not be melted. Okay, so the iron and the sand here would not be melted, and out here the methane and the water would not be melted. They would be solids, and it's from those solids that we end up creating those planets. Okay, so inside the frost line, we don't have any water and ice, but outside we do. That means that I have much more solid material out in this region than I do here. Okay, if I was creating planets, and planetary creation is easier given more and more solids, then I would create many more planets out here, big planets, than I would in here. And that's what we've seen. That's what our simulations show us. Okay, so here is let's see if we can get this guy to go. This is a simulation showing the coalescence of a bunch of objects into fewer objects. And basically, the idea is that this is sort of how the inner solar system was created. And one could watch this for a while, and we'll see that, after a while we start coalescing many, many more objects. Like here, oh, and we're getting really close. There's that little dot. It's coming up closer, and there, oh, we sucked up something. And that's sort of what we would expect to have happen in the inner solar system. This is the frat party that Hal Levinson was talking about in the Planets BBC series. Okay, and if you want to see how this is done, this is the link to get to it. Okay, so, and again, as you can see here, we start off with 200 bodies and they coalesce into two larger ones. Now, the other thing that I want to point out to you is, this is the accretion sort of process going on. Before that, we would have the electrostatic type of attractive situation, and that's exemplified by the ISS experiments, the Don Pettits that I've asked you to take a look at. So I would reference you in terms of that. So that's what these that's what this indication is for. Okay, so again, in these regions, we can coalesce materials together by a number of different ways. Initially, it's through condensation and electrostatics, but then later on, it's through a method of accretion. Okay, alrighty, so now the next step is that the sun gets created, and what ends up happening is I cannot open up the specified file. Okay, so let's pause and we'll start up in. Okay, so back here again, and we're now going to now we are going to try to turn on the solar wind here, and we'll see what happens. So here is a star coming up. I mean, it's a pretty simple thing. But the idea is that we're starting out with a solar nebula that is basically all sorts of gas and dust. And then when the sun turns on, now the sun turns on when the inner core gets to about 10 million degrees Kelvin. And then a lot of energy gets pumped out, right? Just as we see in the daytime sky. Okay, before that, there was lots of gas and dust and you really couldn't see the sun. So let's see if we can get this thing to start again. Okay, so we have a bunch of gas and dust, and then the sun turns on and then blows it all away. Okay, examples of what's going on here is things such as solar sailing, or if you will, the Crookes radiometer, or the photoelectric effect. The idea is that if you hit something with a photon, then you're going to have light pressure. I mean, not light as in heavy and light, but I mean light in terms of, spectra or lights from a lamp or something like that. You're going to have pressure caused by the light hitting the particle and then bouncing back. And it will cause that particle to move, just as we see in the simulation. Okay, boom, all the material goes away, and all you have in the inner solar system is that which you start, the big heavy stuff. Okay, that's all we got left. All right, continuing on, that sort of leads us to this last bit, which is kind of interesting. We'll talk a little bit more about it when we talk about asteroids and that sort of thing, but I want to show you this simulation because it is kind of fun. As you can see, you can turn it on yourself. Oh, I want to go to the other one. I always make that mistake. So let's go here. And I like this one because it basically has the neat statement of kaboom right there. Okay, so you can target a whole bunch of different planets and the moon. It's always more fun to hit the Earth. And you have three choices for the projectile composition. So what I'm doing is I'm sending an asteroid or a comet to Earth and seeing what would happen. Projectile, the comet or asteroid diameter of 5 kilometers. Yeah, it's about the size of the thing that wiped out the dinosaurs. And the projectile velocity, this is a good one to have. It's basically about the same size as the of the escape velocity from the Earth. Okay, so kaboom, let's start it going. And the projectile diameter, tells us the information we input to it. And one of the neat things is it will show a picture of a similar crater on the Earth. Okay, this one being a 100-kilometer impact crater in Quebec. And most of these pictures that we have are basically relatively new. It wasn't until we started doing Earth orbit sensing that we would see pictures that sort of gave us an idea that we actually had craters on the Earth. Okay, so one of the interesting things about this, we created an earthquake magnitude of 10.2, so pretty big. The crater diameter would be as big as the LA Basin and about as deep as the height of the PV Peninsula, not too far away from here. Okay, so let's go return to this picture and let's put in something smaller. Let's put in something the size of, let's see, that which landed in Arizona, and we will make it out of iron. And this is the meteor crater that we would see in in Arizona. So here is an example of one of these type of craters, and it happens pretty quickly. But look at how much energy. I mean, twice the size of the largest nuclear weapon ever blown up. And these type of events happen pretty regularly. Okay, let's see if we can make something even larger. So we'll do kilometers, and let's say we can do 500 and see what happens with that. And we'll make it out of iron again, and we'll kaboom it. And this is called the big one. Now, 500 kilometers is pretty big, but look what it does. Um, that's pretty deep. um, as you can see, uh, well, they'll see it on Mars. It's all over for us. 4,000 kilometer deep crater. I thought the Earth was only like 6,400 kilometers in diameter. So that's a pretty big event. Okay, let's continue on. Um, I can't pronounce this event, but this is the one that occurred a couple of years ago, it being 2016 now. It's kind of amazing the detail that I got about this event. It comes from a couple different sources. Basically, well, the source I got it from was Physics Today, but the source of the information comes from people actually digging up the meteorite that landed in Russia, and video analysis of or analysis of the videos that were created of the event, but also data that is coming from the Nuclear Test Ban Treaty seismographs. And that gives us very good, information on the amount of power that was released by the airburst. It's also very interesting that one can do a very detailed analysis of the history of this asteroid. Just amazing. Look at this, it was created, very early on, and it had some run-ins with the sun. Um, it's just pretty amazing what you can learn from with a little bit of effort. Okay, we've played games with these things. The games being simulations, but these simulations also are reference the idea that things like this could hit us. There are movies made by Hollywood all the time, like Armageddon. Not necessarily correct, but the idea is still there, in that there could be objects that do hit the Earth. There is a program at NASA called the Near Earth Orbiting program. We can go there and take a look at what it looks like. I encourage you to go take a look, see what's there, just for the fun of it. Apophis is a asteroid that was going to scare a lot of people. It was thought that it was going to run into the Earth, but if it does, it's really going to be nighttime for us. But the chances of it hitting us are much, much less, as we have determined the orbit that this asteroid makes in better detail. So we found out that it's going to be a pretty amazing sight when it gets close to the Earth, but it's not going to run into the Earth. Okay. The current analysis of the Barringer crater is indicated here. The amazing thing is if you're anywhere close to it, you might as well, kiss your rear end behind, kiss your rear end goodbye. So, this little factoid here doesn't give one confidence that we know everything that's going on, but then again, the risks are kind of small. But the risk year to year is small, but the risk over a long period of time is quite high. So it's interesting in that regard that it's sort of like airplane crashes. If you have an airplane go down, you have a lot of deaths. But the chances of an event occurring are kind of small. It's sort of, over a century, you end up with the same number of deaths overall. A small fraction of time, small probability that an event will occur, but large numbers of deaths. And then compare that to automobile accidents, which are quite frequent, but with very few deaths at any particular time. So, it's basically you get it one way or the other. Near-Earth or asteroids, we played the simulation game and we got one that was similar to the dinosaurs, and this is the one that's thought to have wiped out the dinosaurs in the Yucatan. And if you look at seismograph recordings of what's going on there, you can see these characteristic craters, very deep down. Other things that are occurring, it's roughly about 300 tons of material, of asteroid material, is sort of floating into the Earth on any particular day. About 10% of that is water. So the oceans, we're getting more and more water as the years go by from just the 30 tons per day. 300 tons per day of, that cigarette smoke soot is running into the Earth every day. It's not the size of an asteroid that's going to wipe out the dinosaurs. No, we're talking about particles that are quite small, and in the evenings you can see them in terms of shooting stars. Okay, so let's see. The last thing I want to talk about is galactic recycling. And basically that is where we start from. We have a star that produces heavy elements from light ones, and it goes supernova. And when it does that, it seeds the gas clouds and allows for a solar system like ours to occur. Remember, our solar system is quite unique in terms of the history of the universe, in that there is lots of dirt, carbon, phosphorus, oxygen. These things are necessary for life. And if we had a solar system being created that was much young, started earlier on, like 4 billion years ago, then there wouldn't be a lot of that material, and it would just be hydrogen and helium. So we should be thankful that we started out, through the universe about halfway through. Last things I want to remind you is that we do have this idea of conservation of angular momentum. And so as our gas cloud condenses and gets smaller, it does speed up, and that is exemplified by, the standard analogy that one uses is an ice skater. And so we will show you, the simulation here. We get smaller and then it speeds up. But the ice skater is sort of, the analogy that we use quite frequently. So, as she, we'll start this again. She puts her arms out, right? And she's going to pull them in and speed up. So going slowly, and then pulls in her arms, and she should speed up, or speed up the rotation. And as she gets her arms really close, she'll spin even faster. So you can do that yourselves. Just sit in a chair that's got, that you can turn around in, and then have somebody spin you up or spin you, and then pull your arms in. You can have that effectively occur to you. Okay, so basically it's very simple for us to create a cloud of gas, and we can have a supernova just smack it and get particles that are no longer just floating around like a cloud in the day sky, with nothing happening to it. But remember that when a cloud gets close to a mountain, it gets compressed, and that is the same sort of thing that's happening with a cloud that gets smacked by a supernova. So these there are regions in the gas cloud now that are no longer uniform, but some are highly densified, if you will, and they're going to start pulling in more material, and that's how it starts. And we have seen that from that lowly beginning, we can create stars and we can create planets from that. Okay, our theory also gives rise to why there are two major planets. Basically, the rock up front is at greater temperatures, and it can be solid at greater temperatures than the ice. And the inner planets have less to draw on than the outer planets as well. So the gravity from these larger planets are able to draw in the hydrogen and helium gases. Now, the theory has improved since then. And so we'll talk about that in the next installment.